Hello everyone and welcome to this analysis of the Threema Secure Messenger, and this is a joint work between Kenneth Paterson, Matteo Scarlata and myself. We're from the Applied Cryptography group at ETH Zurich. So let's start with the first question. What is Threema? So Threema describes itself as being an end-to-end encrypted instant messaging application for both Android and iOS. It boasts more than 11 million private users worldwide, as well as some important organizations that use it, for example, the Swiss government, the Swiss army, and allegedly the Chancellor of Germany, Olaf Scholz. So this makes it a quite interesting target for an analysis. And I'm going to jump right to the analysis itself and describe to you the high-level view of the protocol. So whenever Alice wants to communicate with Bob, they communicate through the end-to-end protocol, which passes through the server. And then, because some metadata is necessary for the server, but we don't want to leak this metadata to any external attacker, the messages are encrypted again using this client-to-server protocol, or C2S for short. So we have 2 layers of encryption, which is actually a quite standard paradigm for messaging applications. You have this in WhatsApp, Signal, and Telegram. So we have to sort of dig deeper into the protocols to see something interesting. So the end-to-end protocol works something like this. So again, Alice and Bob want to communicate with each other. Everyone has their own public and private key pair. And you can think of these as elliptic curve key pairs, more or less curve 2519 key pairs. And assume that Alice knows Bob's public key and vice versa. Then they just do a simple Diffie-Hellman between their 2 keys and they get this encryption key in green. And whenever they want to communicate, now they just send messages encrypted using that key, and that's it. So this is a very simple protocol, or rather, this is a very simple protocol, and because of its simplicity, it does not provide some of the properties that we would like from a messaging application. For example, it doesn't provide any forward secrecy, and it doesn't provide any post-compromise security, because the keys always remain the same. To sort of fix this, in a sense, what Threema did before the fixes is adding forward secrecy on the client-to-server level. And this is done by creating an ephemeral session key between the client and the server, and this is done through an authenticated key exchange. So now Alice, whenever she wants to connect to the server, she establishes a new session key, which sort of protects her against this lack of forward secrecy. I'm going to describe the client-to-server protocol, or rather a single message of the client-to-server protocol. So Alice and the server Alice wants to connect to the server. Alice has her long-term key, which I want to know this is the same key that she uses to communicate with Bob in the end-to-end protocol. And then the Threema server also has a long-term key, which is actually embedded inside Alice's application. They combine these two keys to obtain this authentication key in blue. And then because, again, we want to create an ephemeral session key, each of the party generates an ephemeral key and then combine them to obtain a traffic key in orange here. So you might notice that this traffic key is completely unbound from the identity of Alice. So Alice sort of needs to prove that this traffic key is her traffic key in a sense. So what she does is she takes her ephemeral key, EPKA, and she encrypts it using the authentication key, in a sort of way using the MAC to sign this key. And this creates a value which we call a vouch box. Then Alice, what she does is she just sends this message to the server saying, hey, this is my ephemeral key, I'm Alice, so this is my ID, and here is a value called a vouch box, which sort of says that this EPKA that I just sent you belongs to Alice, belongs to me. Then the server will decrypt all the messages, and if everything works out correctly, then the handshake subprotocol terminates correctly, and the traffic key is accepted for use in the transport subprotocol, where messages are just encrypted using that back and forth between the server and the client. Okay, so now I'm going to describe one of the attacks that we found on Threema. We found 7, more or less. I will point you to the paper in order to see the details regarding the various attacks. But I will describe one of the attacks, which we call the vouchbox forgery attack. And this attack leverages this interesting observation, that whenever Alice wants to communicate with the server, she uses her long-term key and the long-term key of the server to obtain the authentication key earlier. But whenever Alice wants to communicate with Bob, she also uses her long-term key, combining it with Bob's long-term key to obtain an encryption key. And there is no additional step of key derivation in the middle. So you can imagine what happens if Alice, rather than talking to Bob, she's talking to some adversary who somehow claims that their public key corresponds to the key that the server has in the client-to-server protocol. Well, in this case, then the two keys, one being used for the client-to-server protocol and the other one being used for the end-to-end protocol, end up being the same. Now, there's this detail of how does the adversary claim that the public key is theirs without knowing the corresponding private key, but we will discuss that later. And then the question becomes, okay, so we managed to make these two keys collide, then what can we do now? Well, the answer is that now one message from one protocol can be decrypted as a message in another protocol. And this is exactly what we exploit. So imagine that Alice somehow gets social engineered or forced to send a message that actually can be interpreted both as an end-to-end message, but also as an ephemeral key, so an EPK star. And assume that Alice sends that message to the to the attacker who claims that his public key is PKS. Then this message that Alice has just sent to the server corresponds to a valid vouch box that the attacker can then use. And then the attacker now simply authenticates normally to the server saying, hey, I'm Alice, here is my key PK star, and here is a valid vouch box. Because Alice has created a vouch box, this will go through, and the attacker manages to authenticate as Alice to the server. This does not allow access to the end-to-end encrypted messages clearly, but still it does leak some metadata about the messages. So, to recap, this is a client-to-server and end-to-end cross-protocol attack. We use a message from one protocol to break authentication in the other protocol. And the practical consequence of this is that if you sort of send a specific text message to a specific account, you can compromise client authentication forever. And this is quite an unintuitive thing. There are some issues that I want to discuss, some loose ends. So the first one is, how do we find this valid EPK star? The point here being that ephemeral key can be whatever you want. There are 32 bytes of basically random bytes. However, end-to-end messages are not quite random. They have some structure that then this ephemeral key must respect. And in this sense, what we want to do is now we sort of have to find a key pair where the public key has this particular structure. We call this task getting that key. Then the second task is also, how do we as an attacker claim that the server's public key is the same as our public key without knowing the private key? And this task we call the bamboozling. Okay, first task, getting a valid EPK star, is actually computationally intensive because the best way to do this is sort of randomly sample private keys, then compute the public key and see whether the public key respects the characteristics that we want. And empirically, we found that this takes around 2 to the 51 keys through some simulations. And this is actually quite a lot of computation because these are public key operations. So we done some estimates. 8,000 cores for a week on AWS cost around $180,000. We sent this message to Kenny, and Kenny said, yikes. And completely unrelated to this, a couple of days afterwards, Kenny sends a tweet saying, we need to borrow 8,000 cores for a week, and if anyone has some of them lying around, it would be very nice. But after some core hours, some crunching with the cores, we managed to find a valid public key, and then here it has a particularly nice structure. Again, this is discussed more in the paper, so I'll point you to that. And the second task, the bamboozling, is about the adversary being able to claim that the server's public key is their public key. And we did this by sort of abusing a feature of Threema. It's called Threema Gateway. It's an API that allows anyone to sort of create their, to sort of receive and send messages programmatically. You can think of this sort of as an enterprise version of Telegram bot API. And you can register accounts with arbitrary public keys. You can just give an arbitrary public key, and it does not check whether you have the corresponding private key. So, for example, you see here on the top, we have a nice account called LYTAAS, which has a public key. And on the bottom, you see the code of the Android application, which has the server pub key. And you can see that both of them correspond. And some of you might ask, what does LYTAAS stand for? It stands for Lose Your Threema Account as a Service. Yeah. So I want to conclude by saying that Threema actually mitigated all of these attacks. They've been very quick, so we commend them for being very reactive to this to our disclosure. However, I still want to talk about some of the lessons that we can learn from this analysis. So the first one is about rolling your protocol. So Threema did not roll their own crypto, which is already a very nice, is a very good baseline, but they sort of rolled their own protocol in the sense that they tried to create the client-to-server protocol by basing themselves off a known protocol called CurveCP by Daniel Bernstein. And the problem here is that CurveCP actually mandates that messages require specific kinds of nonces which have a particular shape. And this would have mitigated our attacks. So then the question becomes, what does it mean to model a protocol after another one? Because even if the starting protocol is secure, then you have to ensure that your modifications do not affect the security of your new protocol. And then, once again, we have to cite the matrix paper here in the session. We know that there are some vulnerability there were some vulnerability in matrix, and these again were cross-protocol interactions. So this is seems to be a quite common occurrence in messaging applications and other cryptographic applications in general. And then the question is, how do we prevent this kind of things from happening? And the answer is that we have to sort of do a formal analysis of our protocols. But doing an analysis of the single protocol itself is not sufficient. So, because, for example, the end-to-end protocol is quite simple by itself, so it's probably secure. But then what happens when you compose it with the client-to-server protocol? And in addition to this, when Threema sort of added forward security to the messaging application, instead of rehauling their end-to-end protocol, what they did is they slapped it on top of the end-to-end protocol. And now you have another protocol that you have to sort of integrate in this formal proof of the entire system. And Threema recently released a formal security proof of the IBEX protocol, the one that asks for forward secrecy, but there is still this gap where we don't know how the three protocols together interact. And now imagine that someday Threema wants to add the post-compromise security, then maybe they will add it on top, and then this becomes exponentially harder to analyze formally. So to conclude, the lessons that we learn is that, well, don't roll your own crypto, and we all know this, but also try to not roll your own protocols. But if you do, because of course some people will have their core business relying on a cryptographic protocol, then you should be aware of cross-protocol interactions. And more specifically, you should try to do key separation, you should do non-separation or message separation. Try to ensure that a message from one protocol cannot be used in another protocol. Also, you really need provable and proactive security for your protocol. So thank you everyone for listening. If you have any questions, feel free.